name is Kevin Schmidt, and my mentor was Nick Harris. He is just finishing his PhD in microbiology, and I'll be telling you about my experience at SYIP. So a bit of background on his project. He's been working with this reaction. All of these little circles here are enzymes, and he's been working on the biosynthesis of an isonitrile. An isonitrile is this thing right here, a nitrogen triple bonded to a carbon. And since nitrogens typically have 3 bonds, it's an extremely reactive compound. And this right here is a little diagram of the plasmid that we use. The little green arrow here is our SCO-E gene. SCO-E is the yellow enzyme right there, and that's the enzyme that's used to create the isonitrile. So the current project that we're working on over the past month, we were trying to figure out exactly how the isonitrile is formed, and to do this, we are mutating certain residues that are important to the function of SCO-E, and by mutating them, we'll see if the isonitrile is still formed after they're mutated. And this diagram here is crystalline structure of the key catalytic residues that was sent over from MIT. Before I got here, Nick had purified a protein and sent it over to them so that they could map it out. This is a bit of an easier one to see. So we're doing 4 mutations. 3 of them were tyrosines. These 3 right here are tyrosines, and phenylalanine looks very similar to tyrosine, so we're mutating it to that, so it would have like the same structure, but it was different, so we'd still be able to see like it would be different. And the other one we were mutating was arginine, which we mutated that to glutamine because they also look very similar, but it's different. I used a software called SnapGene to modify the sequence of my plasmid. Right here, it's kind of hard to see, but a tyrosine codon is a TAC, but I changed this one to TTC, which is the codon for phenylalanine. So I did 4 of these mutations, with each of the 4 mutations that I needed to do. And one thing we did a lot over this past month was a polymerase chain reaction, which is a process where we replicate a certain sequence that we need. So first we would heat it up to separate the DNA strands. Then we would cool it down so that our primers could anneal to the DNA, and heat it back up again to activate the DNA polymerase to replicate the DNA that we wanted. So the first thing we tried to do was a quick change reaction, which what a quick change is we take those primers that I designed and they anneal to the SCO-E plasmid, and through a PCR they would replicate the entire plasmid just with those 2 primers. So we would just replicate a ton of that new plasmid with the mutation. And so we would do 4 PCRs, 1 for each mutation, with 8 primers, 2 for each mutation. And then we transform it onto competent cells and wait for it to grow. But sadly, the quick change didn't work. It failed, nothing grew, so we had to do something else. So we did a Gibson assembly, which other groups have talked about. Basically, instead of 2 primers replicating the entire plasmid, we have 4 primers per mutation that basically we make 2 halves of the plasmid and then we stick them together to form a full plasmid. So I had to order 2 more primers on the other side of the plasmid to do this. So we would do 8 PCR reactions, and each one would do 1/2 of a plasmid. And after that PCR reaction, we would have to do gel electrophoresis, which is a way to purify that DNA and separate it out. And after the gel electrophoresis, this is the picture that I got. Each band is corresponding to one of the PCR reactions. But one of the bands didn't show up for the 4th one, so that was kind of disappointing because that meant something was wrong, and that meant I can't attach that half to the other half since I only have 1/2, so I only have 3 full plasmids. Thankfully, we were able to troubleshoot, reorder another primer, do the PCR again, and I ended up getting that other band. So we had 4 Gibson assemblies to do. These added together to make the full plasmids. And after we had the full plasmids, we started seed cultures, and we started 3 seed cultures for each mutation because sometimes in a mutation maybe the old plasmids would still be there, so there would be the plasmids with the old mutation, or not the old mutation, just the old SCO-E, but not with the mutation, which isn't what we want. And so after we have those seed cultures, we purify the plasmids, so we just have the plasmids, and final steps were we sent those plasmids off for sequencing. So after they were sent back, we were able to see like if basically the mutation that I made, if it carried over to the new plasmids. And thankfully, one of our 3 plasmids we sent off for sequencing for each of the mutations worked, so we had usable plasmids. And then we transformed it onto a different strain of E. coli, which is better for gene expression. That's the BL21 E. coli strain. Before we were using a strain called XL1 blue, which is better for just producing a lot of plasmid. But we transform it into that other one, then purify the proteins. Sadly, the only step that I got to do for this month, I only got up to getting the sequences back and transforming them. I didn't have time to do these other steps, but basically what would be done after this is after purifying those proteins with the mutations, we would combine it with the substrate necessary for the reaction to form the isonitrile, any other cofactors, and then load it onto the mass spec. And with that, we'd be able to check if the isonitrile was formed, and we'd be able to analyze that data and say, oh, if the isonitrile was formed, then we know that it's not really that important for those tyrosines to be there, or to be tyrosines, because it still worked if it's a phenylalanine. So be able to get more insight into how the isonitrile is formed with the SCO-E reaction. So this is just a picture of all the people at our EBV lab and the Jung lab, all the mentors. And I wanted to thank Suzanne and Carl for organizing the program, all the Nick for being my mentor, and everyone else. Thank you. So I said stick together just for simplicity, but actually what's happening is there is, when we put those fragments together with, we put it together with exonuclease, which chews back at the 5' ends of the DNA strands, and DNA polymerase, the fragments anneal to one another, so like they stick together at these ends where it was chewed back. And then DNA polymerase closes the gaps, and the DNA ligase seals the nicks so that they are sealed together into one plasmid.
Could you explain, do you know what happened, what went wrong, why you were missing that band?
Yes, so
you missed it. Oh.
So this, this primer right here, this was, not this one, but the reverse primer of this. At the beginning we had 3 glycines in a row, which I think that's why it caused some sort of problem. 3 glycines in a row is kind of weird. So we reordered another primer that didn't have that, but it still had that mutation that we needed. So